In this video, we're going to look at how to represent a function as a power series by algebraic manipulation of a geometric series. So let's start with a geometric series. 1 over 1 minus x, the common ratio is x. Let's expand this out. You get 1 plus x plus, every term we multiply by the common ratio to get the next term. So x times x gives us x squared. X squared times x gives us x cubed, and so on. We can write this in summation notation, and we get summation n equals 0 to infinity x to the power of n. And the interval of convergence is absolute value of x less than 1. So in fact, 1 over f of x is equal to 1 over 1 minus x is represented as a sum of a geometric series. This is equal to summation x to the n equals 0 to infinity. This here is a power series. It's a power series because it's powers of x. It's an infinite power series, and the sum of this power series is, we can get that in closed form as 1 over 1 minus x, but only for values of x less than 1. So that means that we can represent this power series as the function 1 over 1 minus x. We can represent the sum of this power series as the function 1 over 1 minus x on this interval, x less than 1, larger than negative 1. All right, so let's look at an example. For example, let's plug in x equals 1/2. If we plug in x equals 1/2 into the sum here, we get 1 over 1 minus 1/2. 1 over 1/2, that gives us 2. Plug in x equals 1/2 wherever we see an x into this power series, so we get 1 plus 1/2 plus 1/2 squared plus 1/2 cubed, and so on. This gives us summation n equals 0 to infinity 1/2 to the power of n. So we have found the sum of this power series. 1 over 1 minus 1/2 is 1 over 1/2. That gives us 2. So what does this say? Well, it means that the sum of this infinite geometric series is 2. We were able to do this because x equals 1/2 is inside the interval of convergence. So let's look at another question. Could we plug in x equals 1.1, for example? Let's do that. So let me erase this, because our space is limited on this page, and plug in x equals 1.1. Well, we get 1 over 1 minus 1.1, which is 1 over negative 0.1, gives us minus 10. That's equal to 1 plus 1.1 plus 1.1 squared plus 1.1 cubed, and so on. In compact notation, n equals 0 to infinity 1.1 to the power of n. Are we allowed to plug in x equals 1.1? Well, the answer is clearly no. You can see here we have a negative quantity, minus 10, and here we have a sum, infinite sum of positive numbers that's going to add up to a positive number. And it's impossible to have the left-hand side be negative and the right-hand side to be positive. So what went wrong? Well, it turns out we can't plug in x equals 1.1 because x equals 1.1 is outside the interval of convergence, is outside interval of convergence, which is this part here, x between 1 and negative 1. So you can only plug in values of x between negative 1 and 1, and for these values of x, this infinite series can be represented by this function 1 over 1 minus x. This function 1 over 1 minus x is a closed form for the sum of this power series. All right, let's look at another example. Here we have represent the function f of x is equal to 1 over 1 plus x cubed as the sum of a power series, and find the interval of convergence. Let's start with the geometric sum formula. So 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and so on. And this is equal to summation n equals 0 to infinity x to the power of n. And the interval of convergence is absolute value of x less than 1 or x less than 1, larger than negative 1. Now let's replace x by negative x cubed. So replace x by minus x cubed. So we get 1 over 1 minus x cubed. Sorry, we get 1 over 1 minus x cubed is equal to 1 times the common ratio. This is now the common ratio, minus x cubed. So we get minus x cubed. Minus x cubed times minus x cubed gives us plus x to the 6. X to the 6 times minus x cubed gives us minus x to the 9, and so on. In compact notation, this is going to be summation n equals 0 to infinity minus x cubed to the power of n. Raise everything to the power of n. Remove the negative sign from inside the brackets. We get n equals 0 to infinity minus 1 to the power of n, x to the power of 3n. Now we know that 1 over 1 plus x cubed is itself a geometric series. It's a geometric series with r, the common ratio, to be minus x cubed. So let's find the interval of convergence for this geometric series. So we have r is equal to minus x cubed, and this geometric series converges for absolute value of r less than 1. So absolute value of minus x cubed less than 1. Let's get rid of the absolute value. Get rid of the minus sign, so we get absolute value of x cubed is less than 1. Now take the third root of both sides, and we get absolute value of x less than 1. Or equivalently, x less than 1, larger than negative 1. This is the interval of convergence. The interval of convergence. The interval of convergence is from negative 1 to 1. So that means the function 1 over 1 plus x cubed, this is now the sum of a power series, a closed form for the sum. This is equal to summation n equals 0 to infinity minus 1 to the power of n, x to the power of 3n. This is only valid for values of x less than 1, larger than negative 1. Now let's give some meaning to this. For example, let's plug in x equals 1/2. So plug x equals 1/2. We're going to get 1 over 1 plus 1 over 8. And that, if we simplify that, that's going to give us 1 over 9 over 8, which is 8 over 9. So simplify this, we get 8 over 9. And this is equal to summation n equals 0 to infinity minus 1 to the power of n times 1/2 to the power of 3n. If we expand this out, plug in n equals 0, the first term is 1. Plug in n equals 1, and we get 1/2 cubed. And plug n equals 2, we get 1/2 to the power of 6 minus 1/2 to the power of 9, and so on. So the sum of this infinite series, this is an infinite series that goes on forever, but it has a finite sum. It converges. That means the infinite series converges to a finite sum, which is 8 over 9. So the reason we were able to do that is because we have a closed form for the sum. But notice, when we plug in x equals 1/2, x equals 1/2 is inside this interval between negative 1 and 1. Could we plug in x equals 1.1? The answer is no. So we can't just plug in x equals 1.1 and say 1 over 1 plus 1.1 cubed is equal to summation n equals 0 to infinity minus 1 to the power of n times 1.1 to the power of 3n. No, we can't do that. The reason is because x equals 1.1 is outside the interval of convergence. That's the reason that we can't represent this infinite series as this sum here. The reason is because x equals 1.1 is outside the interval of convergence. So when we find the functional representation of the sum of a power series, it's very important that we know the interval of convergence, because it's the equation that we come up with is only valid for the values of x inside the interval of convergence. For x equals 1/2, that worked. For x equals 1.1, it doesn't work because it's outside the interval of convergence. All right. So now let's look at another example. So here we have express the function f of x is equal to x squared divided by x plus 4 as a sum of a power series and find the interval of convergence. All right, so let's start by rewriting f of x is equal to x squared divided by x plus 4. Let's rewrite this as x squared times 1 over x plus 4. Now, we need to factor this 4 out from x plus 4 in the denominator to fit the pattern of a geometric sum. The geometric sum has this pattern, 1 over 1 minus x is equal to summation x to the n equals 0 to infinity. So somehow we need to make this 4 a 1, and we do that by factorizing a 4. So let's rewrite x squared divided by 4 plus x. This is equal to x squared times 1 over, factoring the 4 out from the denominator, 4 times 1 plus x over 4. And we can rewrite this as x squared over 4 times 1 over 1 plus x over 4, but we will rewrite it as 1 minus x over 4. And of course, the reason is to fit this pattern of a geometric sum. Now we have 1 over 1 minus the common ratio. All right, so now replace x by minus x to the 4th over 4 into this formula, and we get x squared divided by 4 plus x. This is equal to x squared over 4 times 1 over 1 minus x over 4. And that gives us x squared over 4 times summation n equals 0 to infinity minus x over 4 to the power of n. Now, we can multiply x squared inside the summation. So we're going to get summation n equals 0 to infinity x squared over 4, multiply the whole thing inside the summation, times negative x over 4 to the power of n. We get summation n equals 0 to infinity. Simplifying this, we're going to get x squared over 4 times negative 1 to the power of n, x to the power of n, divided by 4 to the power of n. So simplifying this, we're going to get summation n equals 0 to infinity minus 1 to the power of n, x to the power of n plus 2, and we have 4 times 4 to the power of n, so in the denominator we get 4 to the power of n plus 1. Let's rewrite that on the next page. So we have x squared, x to the power of 2 divided by 4 plus x. This is equal to summation n equals 0 to infinity minus 1 to the power of n times x to the power of n plus 2 divided by 4 to the power of n plus 1. This is the power series, and this is the sum of the power series. So this is sum, and this is the power series. But we have to know, when is this equation valid? When can this power series when can it be represented by this sum in this closed form? We need to find the interval of convergence. So let's go back to how we built up x squared over x plus 4. This is equal to x squared divided by 4 times, we factor the 4 out, times 1 plus x over 4. This is equal to x squared over 4 times 1 minus x over 4. And this is in fact a geometric series. A geometric series with common ratio r is equal to minus x over 4. And it converges when the absolute value of the common ratio is less than 1, when the absolute value of minus x over 4 is less than 1. So let's get rid of the minus sign, so we get x over 4 is less than 1 because the absolute value gets rid of the minus sign. So we get absolute value of x less than 4. And that means x must be between 4 and negative 4. This is the interval of convergence. Interval of convergence. That means that this power series, this infinite power series, can be represented in this closed form, in this functional form, for values of x less than 4, larger than negative 4. So you can see it gives us a tool to find the sum of an infinite series, but only for values of x between 4 and negative 4. All right, so now let's do a bit of review here. The key concept that we had in both of these examples was that we use the geometric series formula 1 divided by 1 minus x is equal to summation n equals 0 to infinity x to the power of n as a building block for developing the power series representation of other functions, such as f of x is equal to x squared over 4 plus x. And I think in the first instance, we had f of x is equal to, let me find it, f of x is equal to 1 over 1 plus x cubed. In both instances, we algebraically manipulated the geometric series formula, and we used it as a building block to develop the power series representation of the function that we were after. All right, thanks.